Hello my dear students, good morning. Now we will continue class with equilibrium chapter. So now we have a Le-Chatelier principle. So without wasting time, what is Le-Chatelier principle? According to Le-Chatelier, okay? According to Le-Chatelier's principle, okay? If we subjected to okay, if we subjected to change in temperature, pressure, or else some concentration, etc., then equilibrium will shift. Equilibrium will shift towards the direction in which that change will nullify. Nullify, or else we can say cancel. Okay, so this is exactly Le-Chatelier principle. According to Le-Chatelier principle, if we subjected to change, means if we made some changes in temperature, pressure, concentration, etc., with some properties, okay, if we change at equilibrium, okay, then equilibrium will shift towards the direction in which that change will nullify or cancel. So if we are subjected to change, means what? If we increase or decrease either this temperature, pressure, or else concentration, then equilibrium will shift towards in opposite direction. Okay, suppose if we are increasing the temperature, then equilibrium will shift towards in which direction that heat absorbs. Okay, that means how much temperature we increased, that have to cancel. So in that direction it will move. Okay, so this is very important. If pressure increases, then what happens? Pressure is inversely proportional to volume. Volume is directly proportional to number of moles. That means if pressure increases, then equilibrium will shift towards the number of moles decrease. In that way, that will cancel or nullify. Okay, so this is the most important thing. So one by one we will see. So first one is, what is that? Effect of pressure first. So this is all what this Le-Chatelier principle gives factors affecting equilibrium. Means if we change pressure, what happens? If we change temperature, what happens? If we change concentration, what happens? Like that. Okay, so if pressure increases, what happen? If pressure decreases, what happen? So that we will understand in effect of pressure on equilibrium. This effect of pressure on what? On equilibrium. So first we will have that what will happen if pressure increases. If pressure increases, what happens? So as I said, Boyle's law and Avogadro's law you should know. So Boyle's law means what? P is inversely proportional to volume. And you have to remember Avogadro's law. Volume is directly proportional to number of moles. So P is inversely proportional to volume and volume is directly proportional to number of moles. Those two things you have to remember, sir, everyone. So why you have to remember? I told you already. So if pressure increases, then what happens? Pressure when increases, certainly if you are taking some substances, means reactants in a vessel, so you are increasing pressure like this, you are applying some pressure, certainly volume what happen? Will decrease. Certainly volume decreases, so initially this is V1 and now this become V2 when you applied pressure. So what happened? V1 is greater than V2, so volume what happened? Decreased. Volume decreases. Certainly when volume decrease, then number of moles will decrease. This is very clear. So when pressure increases, then number of moles will decrease. So reactants will decrease. Okay, so here what happens? What I can say here, if pressure increases at equilibrium, then equilibrium will shift. Equilibrium will shifts towards the direction in which volume decrease or number of moles decrease. This is very important. So when you are increasing pressure, when pressure increased, then equilibrium shifts towards the direction in which volume decrease or number of moles decrease. Okay, so this is the most important. So I'll give you one example. SO2 plus O2 equilibrium to SO3. In this equilibrium reaction, so reactant consists of SO2 and O2 are 3 moles. 2 SO2 and O2, 3 moles. And product how many moles? 2 moles. Okay. So to happen this reaction means to get more SO3, what pressure required? See here, 3 moles converted to 2 moles. That means number of moles decreased. Certainly, what required here? Volume should decrease. That means pressure should increase. So, in a particular reaction, so I am considering forward reaction because they are asking me what pressure required to get more SO3, or the pressure favored for the forward reaction means, okay, then you have to check the number of moles of both reactants and products. So reactant moles how many? 3. Products moles how many? 2. So okay, number of moles decreased. Certainly what you can say, yes, high pressure required, you can say. Understood? Because number of moles, what happened here? Decreased like that. Okay. For backward reaction, then low pressure required. In backward reaction, if they ask what is the favorable pressure for the backward reaction means, then you have to check the number of moles. Okay, in backward reaction, 2 moles converted to 3 moles. That means number of moles is increasing in back reaction. In backward reaction, number of moles increasing, so pressure should decrease. Simple. So low pressure favors. Got it, sir, clearly? So this is about effect of pressure. That means when pressure increase, what happen? Then equilibrium will shift towards the direction in which number of moles decrease or volume decrease. Then what we will do now? Next, it's very simple. When if pressure decreasing, well, certainly you can say equilibrium will shifts towards the number of moles increase, pressure decrease. So if pressure decrease, then equilibrium will shift. Equilibrium will shifts towards number of moles. Okay, number of moles increase, you can say. So I'll give you one example, like anything like 2a plus b gives rise to 3c plus 2d. In this, this is a forward reaction actually, forward reaction. So to get more products, to get what? More products. Favorable pressure is, if they ask, very simple. In reactants, how many moles you have? 2 plus 1. So 3 moles you have. How I am saying 3 moles, understood? Here you have 2, here 1. So 2 plus 1, 3 moles. Here how many moles you have? 5 moles. 5 moles you have. Here 3 moles and here 2 moles. 5 moles you have. So number of moles, what happened? 3 moles became 5 moles here. So number of moles increased. So therefore, what is required? Low pressure favors, since what is the reason? since number of moles increase, uh, reactants to products. Number of moles what happened? Increase. That's why. Okay. Next, let's see what is the effect of temperature. Very simple. Effect of temperature. Two things we will learn. Again, increase in temperature on equilibrium. What happens? Decrease in temperature. Decrease in temperature. What happens? Very simple. Decrease in temperature when required, or increase in temperature when required. It's very simple. Suppose if a reaction is endothermic, suppose A plus B gives rise to C plus D. This delta H is a positive. You know this thermodynamics. Delta H positive means what? This is endothermic. So here these are enthalpy of reactants. Here enthalpy of products. Endothermic means what is the meaning? Enthalpy of reactants is less than enthalpy of products, because delta H is nothing but enthalpy of products minus enthalpy of reactants. If reactants enthalpy is less, then only delta H you will get positive. So this is endothermic. So in endothermic reactions, enthalpy of reactants less. Certainly, in this particular reaction, what required? So for forward reaction, increase in temperature favors. Why increase in temperature favors? Because reactants heat is less, products heat is more. Certainly, you need more temperature to convert AB into CD. Getting what I am saying? So, increasing temperature favors endothermic reaction. Simple. So, what you have to conclude? Here you can conclude endothermic. See, forward reaction is endo. So, for forward reaction, endo. So, for forward reaction, increasing temperature favor. If they ask for backward reaction, what temperature required means low temperature, because forward reaction is endo, therefore backward reaction is exo. This is very, very important. So endothermic reactions, for endothermic reactions, increase in temperature required. For what? For endothermic reactions, increase in temperature favors. For exothermic reactions, decrease in temperature. So decrease in temperature favors. So to understand effect of temperature, they must give this particular representation about delta H. They must say, if delta H is positive, okay, forward reaction is positive, okay, forward reaction is endo, so okay, for forward reaction to happen, more temperature required. Okay, forward reaction is exo, so okay, exo means reactants already have more energy. Certainly you have no need to increase the temperature, you have to decrease the temperature. Very simple. Decrease in temperature, as I said, favors exothermic. Simple. So these two, this is effect of temperature. Very clear. So as I said, these 2 points are very important. Please note it down. For endothermic reaction, increase in temperature favors. For exothermic reaction, decrease in temperature favors. Okay. So this is about what effect of temperature, like this. 2NO plus O2 equilibrium, 2NO2, they given like this, and delta H is something plus 194 kilojoules, like that. So this is endothermic, plus you have no endothermic. So to get or to prepare NO2, high temperature favors. Example. What is the reason behind it? Because formation of NO2 is endo. Endo means high temperature favors, that's it. Okay. As I told you in previous, N2 plus 3H2 Haber's process ammonia preparation gives rise to 2NH3. Here delta H is a negative. Okay. So here exothermic reaction. Minus 92 something is the value. Okay. So exothermic. So for preparation of NH3, what required? Low temperature favors. What temperature favors? Low temperature favors. Why low temperature favors? Because ammonia formation is exothermic, means reactants enthalpy is more. Because as I said, enthalpy is changes, enthalpy of products minus enthalpy of reactants. It should be negative. That means enthalpy of reactant should be more. That means these already have more heat, N2 and H2. Certainly you have no need to increase again. So exothermic reactions, for exothermic reactions, low temperature favors. For endothermic reactions, what? High temperature favors. So as I said, you have to check for the particular reaction what they are asking. They are asking temperature favorable for forward reaction or backward reaction. Then you have to check forward reaction is exo or endo. If they ask backward reaction is exo or endo. Then you have to apply this. That's it. This is about effect of what? Temperature. Effect of what? Temperature. Next, effect of concentration. Effect of what, sir? Concentration. Okay. So concentration effect to understand law of mass action. If you know, it's very simple. So next one is effect of temperature. Oh shit, this is over now. Sorry. Effect of concentration. Concentration of what? Concentration of either reactants or products. How they are affecting equilibrium. Means here four things you have to remember. First two things about reactants. If reactant concentration increase, what happen? If reactant concentration decrease, what happen? If product concentration increase, what happen? If product concentration decrease, what happen? These four things you have to remember. Got it, everyone? So this is the most important thing. So 4 points you have to understand. For that is very clear. Rate of forward reaction is equals to Kf into concentration of reactants, right? And rate of backward reaction is equals to Kb into concentration of products. Rf is equals to Kf into concentration of reactants, and Rb is equals to Kb into concentration of products. If you know this, you can say now. So if reactant concentration increases, then rate of forward reaction increases. In this case, forward reaction happen. Correct? Huh? So in this case, suppose this is case 1. In this case, so when reactant concentration increases, rate of forward reaction increases. Therefore, forward reaction takes place. Understand? Rate of forward reaction increases means equilibrium will shift towards formation of products. Formation of products is nothing but forward reaction. Very simple. Got it clearly? So when reactant concentration increases, then rate of forward reaction increases. That means that is forward reaction favors. That means equilibrium shifts towards formation of products. This you can say, that means equilibrium will shifts towards formation of what? Formation of products. You can say this. So this is one. So next is rate of forward reaction is equals to Kf into concentration of reactants, right? So when the reactant concentration increases, I told you, now when the reactant concentration decreased. When the reactant concentration decreased, then rate of forward reaction will decrease. Forward reaction rate is decreased, means backward reaction happen or not. So very clear. So reactant concentration increases, forward reaction. Product concentration increases, backward reaction. Very simple. When stomach is empty, you have more reactants. This is forward reaction. You eat fast. If reactants are less, that means product is more, then backward reaction, omitting happen. Very simple. So when reactants are more, you have a great food in front of you, your favorite food you have in front of you, then forward reaction will be fast or slow? Fast. So when the reactant concentration increases, so eating process, I am saying forward reaction. Okay. So reactant concentration increases, forward reaction. So now reactant concentration if you decrease, then what happens? So here very clear, if reactant concentration decreases, then rate of forward reaction decreases, therefore backward reaction favors. Backward reaction favors. That's it. So if I know about these two, so that I can say here next point, number 3. So 2 points about reactant concentration increase and reactant concentration decrease. Now if product concentration is more, then rate of backward reaction is increases. So these 2 and 3 are identical. Next 4, that means what reaction favors? Backward reaction favors. 4, rate of backward reaction is equals to Kb into concentration of product actually. So product concentration decreases, then rate of backward reaction decreases. So when product concentration is less, certainly as I said in previous eating example, product concentration is less, then forward reaction, we eat more. When product is not there inside, you feel hungry, then you eat fast or not. Eating process is forward reaction, omitting process is backward reaction. So when product is less, certainly forward reaction. So like that you have to simply remember. Then 4 and 1 are same. Okay. So 4 and 1 are same. This 2 and 3 are same. Means very simple. When reactant concentration decrease or product concentration increase, then favors backward reaction. Reactant concentration increase or product concentration is decrease, then what favors? What? Forward reaction favors for this. Because backward reaction slow, that means forward reaction is fast. Forward reaction means reactant converts to products. So these two are about effect of concentration, effect of pressure, effect of temperature, effect of concentration. 4 points we discussed. So here these two are very important. 2 and 3 means understood. This is 2 and this is 3. It's very clear. So you can write, if reactant concentration increases or product concentration decreases, then forward, simply write down, short way, forward reaction. Okay. Next, reactant concentration decrease or else product concentration increase, then backward, simply write down these two, everyone. When reactant concentration increase, product concentration decrease, forward. When reactant concentration decrease, product concentration increase, backward. These two are very, very important. Please note it down. Okay. So next we will go for last and final in this. Almost we discussed many things. Okay. Effect of addition of catalyst. If catalyst is there, no change in position of equilibrium. But if you use a positive catalyst, then attainment of equilibrium faster. That's it. So that is next is that effect of catalyst. So no catalyst effect, I can say. No catalyst effect on what? Equilibrium position. Means if you add catalyst, no change in the position of equilibrium, but attainment of equilibrium faster. That's it. So this is about effect of catalyst. Next, last and final, effect of addition of inert gas. Hope you understood that. Catalyst will speed up the reaction, so it won't change the final destination. So when equilibrium exists, that won't change. So it gives some speed. Who? Catalyst. So catalyst will not alter, will not change the position of equilibrium, but it increases the speed of reaction. That's it. Okay, so effect of addition of inert gas. Two things you will discuss. Effect of addition of inert gas. Effect of addition of inert gas at constant volume, and next at constant pressure. Two things we will discuss. So addition of inert gas at constant volume, no effect. That is, no change in position of equilibrium when you add inert gas at constant volume. Simple thing, volume is directly proportional to number of moles. If volume constant, the number of moles no change. If number of moles is not changing, then there is no effect of equilibrium position. Got it clearly? But at constant pressure, if inert gas added, then what happens? If inert gas added at constant pressure, then equilibrium, then what happens actually first? Then volume increases. Correct? Volume is not fixed, so pressure constant. So you are adding inert gas, means inert gas are highly diffusible. So volume, what happened? Increase. So volume increase, then what happened? Then equilibrium will shift. Equilibrium will shift towards the direction in which volume increased already. So volume is directly proportional to number of moles. So in which number of moles increases. Number of moles increases. This is the most important thing. Read carefully. If you have any doubt, still you please ask me. If inert gas added at constant pressure, then volume increases. Then equilibrium will shift towards the direction in which number of moles increase. This is very clear. Is it clear? Why, sir? Equilibrium is shifting towards the number of moles increase. The only reason here, volume increases. Certainly, number of moles what happen? Increases. Certainly, equilibrium will shift towards the increase in number of moles. That's it. Got it, everyone? So this is very clear. So this is effect of addition of inert gas. Effect of addition of inert gas. Is there an effect of catalyst on equilibrium? No. Important concept. Okay. Of course, I know ionic equilibrium must complete today. I know that. So that will complete tomorrow, ionic equilibrium. So one day is lagging, no problem. So tomorrow also one day. So for that, what I told you already, I will do one extra video, I said. Otherwise, we will have, actually I told you in previous also, some laptop problem is there, I said. That's why I am not doing that online class, I said. So these all the things. So you have to consider. Please, you just try to understand everything. Focus on studies only. Okay, that is very important.
So effect of catalyst, everything important. So please write it down all these things. So very important for us this concept, because based on this concept you will have one numerical. So effect of pressure we have, effect of concentration, effect of temperature, effect of catalyst, effect of addition of inert gas, like that. So they'll ask questions like this: H2 plus I2 equilibrium 2HI. Shit. 2HI. Then for this, what is the effect of pressure, like that they'll ask you. Here how many moles you have? 2 moles of reactant. Here how many moles of products you have? 2 moles. Is there any change in number of moles? No change in number of moles. So for this kind of reaction, there is no effect of pressure. There is no effect of pressure on this particular reaction, because number of moles remains same in both reactants and products. So what I am trying to tell you, if the number of moles, if the number of moles are same in both reactants and products, then there is no effect of pressure. If number of moles increasing, low pressure favor in a forward rate, in any reaction, either forward or backward, what they are asking, they ask like this: what is the pressure effect on forward reaction? Otherwise, what is the pressure effect in product formation? Like that, especially they will mention. Don't worry. Okay, so like that. And one more important reaction, one more important thing I will give you like this. Okay, yeah. Any reaction, sir, A plus B gives rise to C plus D. Here, equilibrium constant is K1. So for C plus D gives rise to A plus B, what is the equilibrium constant? Means 1 by K1. 1 by K1. Remember, this is one example. I'll give you everything, no problem. Okay. Second example, example 2. A plus B gives rise to some C plus Y. It's just C. Okay. C. Then here it's K1 or K something else. Now reaction half A plus half B is equals to like half C. So reaction half. Then you have to take root K1. Root K1. Why, sir? See, for the first reaction, what is K1? K1 is equals to concentration of C by concentration of A into concentration of B. Here K1, so suppose this is, this is K2. K2 is equals to, as I said, root K1. So how this came, I tell you. What is K2 now? So K2 means now, or K2 means it is concentration of C power half, concentration of A power half, and concentration of B power half. Okay, so if I square this one, so squaring on both sides, what I will have? K2 square is equals to concentration of C by concentration of A into concentration of B. Now these both are same. So what I can say, therefore, from this one and this one became same. So K2 square is equals to K1. So what I can say, K2 is equals to root K1, this one. So here I will give you those 2 points. What are those here? First point, if reaction reversed, then equilibrium constant. If reaction reversed, then equilibrium constant should be 1 by initial constant, like this. Okay, understood everyone? Next, if reaction halved, then what happened? Then some K2 is equals to root K1. If reaction halved, then root K1. This K1 is what? Initial equilibrium constant. K2 after half the reaction, this is the equilibrium constant. They'll ask questions like this, very very important. If reaction multiplied with some number, then you have to take as power. With what number you are multiplying, that you have to take as power, very very important. You please write it down. Okay, so when there will be no change, no effect of pressure, I told you, please note it down. Now next point is the most important. If reaction, if what I'm saying, if reaction multiplied with some, if reaction, see maybe you cannot see properly, if reaction reversed, then equilibrium constant should be 1 by, you have to take, and if reaction half, then final equilibrium constant will be root k1, root of initial equilibrium constant, like that you have to remember. So if reaction multiplied with some number, then K2 is equal to K1 power, but that particular number with what you multiplied. This n is number, n is number with what you multiplied to that reaction. So as I said in previous, A plus B gives rise to C. This is K1, equilibrium constant for this reaction. Okay, so now 2A plus B, 2A plus B, then 2A plus 2B gives us to 2C. For this, what is K2 means? K1 square. You multiply it with what number? 2. That 2 is you have here as power. If you multiply it with some 4, K1 power 4, like that. Now, one more thing. Okay, suppose A plus B gives rise to C plus D. Okay, C plus D gives rise to some M plus N. Then here is a K1, here equilibrium constant K2. Important examples all this. This is example 3 and this is example 4. Okay, then A plus B gives rise to M plus N. M plus N. Okay, for this K3. Then what is K3 means? K3 is equals to K1 into K2. Remember this. These points are very important. So for this example 4, what you will say? If two reactions added, then what must be K3? Then K3 or equilibrium constant for resulting reaction. For what, sir? Resulting reaction will be what? K1 into K2. So here I told you very clearly, if two reactions added, then you have to take multiplication of the equilibrium constant. Don't think these two reactions added, so equilibrium constants must be added. So few people will think K3 is equals to K1 plus K2. So equations added, but equilibrium constants means you have to take concentrations of products by concentration of reactants. So when you take a product, then only you will get K3. So remember, blindly you can say if two reactions added, these two reactions added, no, opposite to cancel. Got it clearly? Understood? So this is very important. When reaction reversed, 1 by. When reaction half, root. When reaction multiplied with some number, that number you have to take as power for the initial one, initial equilibrium constant. When two reactions were added, then K1 into K2 for K3. Three reactions added, K4 you will have. Resulting is a K4 now because you added three reactions. So 1, 2, 3. K1 into K2 into K3. Like that, very simple. One reaction written, one reaction is squared and both you added for the resulting reaction. Then K3 is equals to K1 into K2 square. When I said When first reaction you written as it is, second reaction you multiplied with 2, and both reactions you added and you got a third reaction. Then what is a K3 means K1 into K2 square. Got it clearly? Clear? If you multiply with some number like this into 2, if this reaction, and both were added now. So for this reaction they are asking what is K3. Then K3 is equals to K1 into K2. So based on this also you will have numericals. Please remember. So I repeat, write down all these things. When two reactions added, then equilibrium constant for the third reaction should be multiplication or product of those added reactions. When reaction multiplied with some number, then equilibrium constant for the resulting reaction after multiplication with some number is equals to initial equilibrium constant power that number, what number you used for multiplication. Very clear. Okay, next, over sir, about all those things. Only thing is you have to practice, very important. Next is ionic equilibrium. Here in ionic equilibrium you have simply first acid base theories, because ionic equilibrium chapter we can also call acids and bases. Acids and bases. So I'll give you simple way about acids and bases. You please go through those, very important. First you have Mr. Arrhenius acid and base. What is Arrhenius acid? The substance which dissolve in water and release H plus ions to water. Very simple. Okay, I repeat, Arrhenius acid means substance which dissolve in water and release H plus ions to water. That is Arrhenius acid. Very simple. Okay, some examples. No need actually, but this is not much important. But we have to see here it will give Cl minus and H3O plus. So this HCl you can call as Arrhenius acid, but Arrhenius acids just limited for the substances which dissolve in water. So Arrhenius acid we cannot apply for the substances who are insoluble in water. Okay, so Arrhenius theory is restricted only for the acids or bases who dissolve in water. So what according to Arrhenius means the substance which release H plus ions to water, like that. So you can say what is Arrhenius base now. Same, ulta write down. Substance which dissolve in water and release OH minus. Release, same, dissolve in water and release OH minus ions to water. That's it. So this is about Arrhenius base. This is about Arrhenius acid. So many things like NaOH, like that. NaOH will dissolve in water and release OH minus to water. Correct? So NaOH, any base like OH minus with water, it releases what? OH minus or not? OH minus concentration increases. So this is about Arrhenius acid. Simply I will tell you here one more theory. What is that? Bronsted acid and Bronsted base. So our first year notes is important. So if you have a first year notes properly, please go through that. Bronsted, because it is restricted for the substances who are dissolved in water. So what about the substances which are insoluble in water? So to overcome those kind of limitations, this Bronsted acid base theory came. So simple two things I will give you. Bronsted acid, simply Bronsted-Lowry acid base theory. Simply Bronsted acid we call. Bronsted acid means H plus ion or we call that as a proton donor. Proton donor is allogenous acid. Remember this. What is this? Proton donor. Okay. What is Bronsted base? Bronsted base means H plus ion acceptor. H plus ion acceptor is a Bronsted base. Please remember these two. Okay. So HCl when react with NH3, you will get Cl minus plus NH4 plus, like this. So here HCl is a Bronsted acid. Bronsted acid. And Cl minus, I told you, I'll tell you about that. Why this is called as a Bronsted acid means very simple. See, if you see HCl here, HCl, so H plus and Cl minus. So it became Cl minus, so that H plus donated to NH3. So this HCl is a Bronsted acid, this NH3 is a Bronsted base. Bronsted base. This Cl minus is now conjugate base. What is that? Conjugate base. HCl and Cl minus are a pair which exactly differ by one proton. Which exactly differ by how many proton? One proton. So HCl and Cl minus are called acid base pair. But what we call that as particularly conjugate acid base pair. Very important. So HCl and the Cl minus are conjugate acid base pair. So what is conjugate acid base pair? The pair of substances which exactly differ by one proton. Correct, sir? Clear? So this is about a Bronsted acid base theory. Simple. So here you have to remember one more thing. Strong acid has weak conjugate base and weak acid has strong conjugate base. Ulta. If acid is strong, its conjugate base is weak. Okay, so that we will say how they are dissociating in water. So what is the ease of donating tendency of H plus? That decide strong or weak. Same way you can apply for base. So this is NH3, strong base. NH4 plus, that is weak. Yeah, I'll tell you about weak or strong. Okay, so this is conjugate acid. Conjugate acid for whom? This Bronsted base. NH3 and NH4 plus both are conjugate acid base pair because they are differed by one proton. That is very important. So please write it down all those things. Okay, so this is about allogenous acid as well as this Bronsted acid base. Okay, so what is a Bronsted acid and base? Bronsted acid means proton donor. Okay, proton donor. Okay, differed by what? One proton. Remember? So I told you how to decide strength of acid in our previous revision class. I told you electronegativity increases of whom? Central atom. Then acidic character, what it said? Acidic character increases. Or else one more thing I said. Oxidation state of central atom increases, then acidic nature increases. Theoretically we can come to know like this. Otherwise that acid won't say I am strong, some acid won't say I am weak. How we decide? Practically we will decide. We will add into water and how they are dissociating. See, few acids if you add in water, they give some sound like that. They are strong, means they are dissociating. So they are donating H plus ions easily. So practically you can say, but we cannot do practical in NEET exam or JEE exam or CET exam. Correct? Huh? So how we decide? By these two. Suppose HClO4 you have, H2SO4 you have. So this is strong acid than this. Of course this is also strong comparatively. So HClO4, this is acid, strong acid. Now ClO4 minus you have. So this is conjugate base to whom? This one. But this is weak. What is W? Weak conjugate base to this HClO4. H2SO4. This is also strong acid, but HClO4 and H2SO4, if you compare, HClO4 is strong acid. How I said? Central atoms you have to see. Your central atom is chlorine, your central atom is sulfur. So chlorine is more electronegative. I told you chlorine electronegativity is 3 and the sulfur is 2.5. Sorry, 2.5. So more electronegative, more acidic. So HClO4 is more acidic than H2SO4. Now this H2SO4 has what conjugate base? HSO4 minus. HSO4 minus can have conjugate base because basicity I told you H2SO4 2. So this H2SO4 can donate 2 H plus ions. This is a H2SO4 strong acid. This is weak conjugate base, and this can have one more SO4 minus 2. So here you have to remember these two. This and this cannot be a this cannot be a conjugate acid base pair. This one with this, not conjugate acid base pair. These two conjugate base pairs, yes, because differed by one proton. These two conjugate acid base pair, yes, differed by one proton. So this is about conjugate acid base pairs. Okay. So how to identify conjugate acid base pairs? I told you. Okay. So this is about what we have. Next one is, what is that? Simply I'll give you now Levis acid base theory. Here maybe you have some problem to see. What is simply Levis acid? Simple. Bronsted acid base theory also some drawbacks. What Bronsted said, proton donor is acid, but some acids don't have hydrogen. Then how they can donate H plus? Like SO3, SO2, Cl2O7, they are all acids, but they cannot donate proton. So we cannot say their acidic character or basic character. See, here suppose you have like here I give Cl2O7, SO2, SO3. These are acids, but not Bronsted acids. Why? Bronsted acid means that have to donate H plus, like some non-metals, Na2O, CaO, and some Al2O3, and all these. These are bases. Of course, this have an amphoteric, but just simply I am giving. Okay, base. Now, otherwise, just remove this. Or any alkali metals and alkaline earth metals like MgO and all. So these are not Bronsted acids and bases. So Bronsted failed to explain acids and basic characters of this kind. So here are some limitations we have. So those limitations we have to overcome. For that, Levis acid base theory came. What is Levis acid? Simply I'll tell you, lone pair or simply electron pair acceptor. What is EP? Electron pair. Lone pair or some negative charge like that. Acceptor is Levis acid. What is a Levis base? Levis base means simply electron pair donor. Very simple. Levis base means electron donating. Simply electron donating means these are electron rich. So these are electron donating groups, EDZ. These are electron withdrawing groups. These are poor. Who are poor? Levis acids. Levis acids you know already, where like electrophiles, Levis acids. Like nucleophiles, Levis bases. Because nucleophiles are rich, they attract positive charge. So I was given previously, please go through those list of Levis acids and Levis bases. I won't repeat. In our next class about pH, buffer solution, and some salt hydrolysis about, and one more, that solubility product we will discuss in our next class. And please remember, here also I was given some list of conjugate acid base pairs. Please go through that. And these 2 points are very important. Electronegativity increases, acidic character increases. Oxidation state increases, then acidic character increases. Please remember all these things. Okay, sir? So you have to concentrate more and prepare well, don't worry. Okay, so maximum you have to cover all kinds of concepts. Please take care and practice properly. All the best.